Because when you do like this, for me it's like so, you know, but for you it's yes, right? That's interesting. So when I look at you when I lecture and I see all of you do like this, say maybe they don't really understand, but that's not what you mean. Huh? No, strange, huh? Body language. Should we start?
5 minutes.
5 minutes?
We
Yeah.
have some interaction, asking about something
Yes.
we did yesterday. and
Yes.
then we'll start.
It's a good idea. So did you have time to digest what we did yesterday and the day before? Somehow? And did it raise new questions? Not so much? Yes? Yeah? No? It's difficult for me to do it, you know, I have to train. So then I suggest that we start today. So now, after our first step through the Alpine Himalayan belt across the Western Alps, construction of the orogenic wedge, now we're going to move to Himalaya Tibet, which will illustrate construction of an orogenic plateau. So if I summarize, close to the axis of rotation of the plate that controlled opening of the Central Atlantic and then South Atlantic, well, the Western Alps is a narrow orogeny belt with a triangular shape, wedge shape. And it's constructed by burial and exhumation of units along the plate boundary, coastal units, oceanic and continental, that were decoupled from the downgoing slab. That's what we've shown yesterday. So what happens to the Himalaya Tibet? Do we find similar type of record, geological record? Well, obviously the structure looks different. It's a much wider belt with a higher topography at the front and then the plateau at the rear. And we related that the width of the belt to the position far from the rotation axis. So how does it look like? And one of the questions we're going to ask is, where does this material come from? Material that constitutes the thick crust beneath Tibet. Where does it go? You know, what is its history? Although we don't see it very well, because it's underneath the plateau. So in terms of previous work, rapidly, always the same guy, Argan, proposed one century ago that the Tibet plateau was underlain by a zone of thick crust, thick Indian crust, that was down-thrusted below the Eurasian crust, with the Himalayas forming the front of that zone of thick crust. So we just move several tens of years, and then we have the homogeneous lithospheric thickening model, which was proposed after the indentation, the punch model, rigid indentation of India into Eurasia. And here the idea was that after collision, thickening would be homogeneous at the lithospheric scale. So the crust and the mantle lithosphere, the lithospheric mantle, will thicken homogeneously. But in the same years, some other authors said, okay, maybe you have thickening of the crust, but at the same time, the lithospheric mantle might still be going into subduction. So that was the first idea that the crust and the lithospheric mantle could be decoupled. So this leads to these issues that we're going to address: how we can relate plate kinematics and orogenic evolution, which type of rocks, metamorphic rocks, are generated and how are they exhumed during orogenic evolution, and how does it relate to topography and tectonics. So I just remind you about this indentation model, rigid in India, punching soft Eurasia with extrusion of blocks, and that provided a nice way to correlate plate kinematics with continental deformation. But the main assumption here is that India is rigid and Eurasia is weak. So how do we justify that? And that deformation is very localized along lithospheric, crustal to lithospheric shear zones that should be vertical. What this doesn't account for is the crustal thickening and topography, which are first order features here. So that's obviously something is missing in that model. But still, afterwards, researchers kept nourishing this model, looking at current day displacement of point with a GPS, a global positioning system network, with stations put in different places that allow to reconstruct the displacement vector. And again, this is the same as when you look at satellite images. These are mostly measured by satellite. At satellite, they look at the Earth from the top. So it's difficult to measure vertical motion. It's more adapted to measure horizontal motion. But we see here the vertical motion indirectly. So, but let's first analyze this image. So that's the reference frame. That's 20 millimeter per year, so to 2 centimeters per year. The Indian plate is moving like this. You might not see it, but there is an uncertainty circle around that, or ellipse around that vector. So that's the motion of India relative to Eurasia fixed. It's always relative motion. And you see that here, across the topographic front, the vector changes its norm, right? It goes from this size to this size. What does that mean? Slow down, yes. But if, okay, that's a good point, in terms of vector, it slows down. But where does the material go if it slows down? So that in between this point and this point, it's not just a matter of velocity, it's a matter of mass conservation. So if there's a point here, and I'm moving faster than he's moving, what's happening in the material of the in between? Compression, that's the tectonics word. Huh? So that's compression, meaning, and what you have in mind? Thickening. That's it. So short, horizontal shortening in terms of deformation, vertical thickening, compression. I accept it. No? So you see indirectly vertical motion here. And crustal thickening should be then followed by isostasy, topography. So we have here a good correlation between the displacement field, kinematics, deformation, and topography. But then what happens? You see the vectors change also orientation, and they move from north-south to east-west. So maybe I should have started with that. At first order, you see a change in orientation of the vectors from north-south to east-west. What do you think? Compared to this model, which is actually, does that fit that model? From north-south to east-west. Yeah? At first order, it looks like it fits, right? You have a change in displacement of material from north-south to east-west. So a transfer of displacement from north-south to east-west. So at first order, this current day displacement field looks like it matches the indentation model. And then, if we analyze further, then we see that that's not enough. There is shortening here that is accommodated by thickening and not only by extrusion. The material not only goes north, south, east, west, it also goes on the vertical dimension. And it's more compelling when you look at here. On the eastern side of the Tibet plateau, you have the norm of the vector is here small and then big again. What is happening here to the material? It corresponds to the topographic front on eastern Tibet. Goes from high to low. So if a point here is moving faster than me, what's happening to the material in between on the horizontal scale? Stretching, horizontal stretching. And what happens in the vertical dimension? Thinning. So in other words, it looks like a wave here. You have thickening here and then shortening here. So this idea of rigid blocks is not matching that field. At first order, if you just look at the orientation, okay, north, south, east, west, that works. But there's more than that. It's north, south, thickening, thinning. So we'll come back to that. Just a quick view of what this guy, Taponnier, he recently died. He was a very famous French tectonics geodynamics guy, and his work was very influential. And so influential that in the last years, he went, I think, too fast. Again, this idea was brilliant. It's made very much stimulation in the community. But when you look at this picture, so there he sort of accounted for crustal thickening and lithospheric thickening. Crust is in purple and the lithosphere is in green. So it changed it a bit from his view only from the horizontal plane. Then he also added magmatism. All the red blobs are plutonic rocks that he associates here with subduction zones. So it's mostly arc magmatism. And how does he explain the Tibet plateau from this sketch? Maybe I should have asked you that question. How can we explain a plateau? What limits the thickness, the topography of mountains? And what limits, if we say, can we turn this question somehow differently? What limits the altitude of a mountain, do you think? What are the processes that we have in store? Sorry?
So the force is major contributor to elevation, because higher the force is, more will be the elevation of the...
Which forces?
The collisional...
Okay, the plate tectonic force. Okay, a plate tectonic force. So if you take a shovel and with sand and you push the shovel, is there a limit to the size of the sand pile? Gravity. So there is at some point a balance between gravity and plate tectonics. That's one solution. Lithospheric delamination might also promote high topography, but will that limit topography? See, it's slightly different. What about erosion? Erosion might also flatten the mountains.
Gravitational collapse.
Gravitational collapse, but that's, yes, that's somehow the idea of having gravity competing with plate tectonics forces. Okay, we're there yet. But is it what is implied in this reconstruction here? What do we see? One subduction here, another one here with a question mark. Huh? Some question here. Another one here, another one here. And for each subduction, a wedge. The implication here is that in this model, the plateau is explained by juxtaposition of orogenic wedges. There's one wedge, and then another one, and another one, each one related to a subduction. And that was the idea that each suture would correspond to one plate closure, right? So one suture, one plate. 1, 2, 3, 4, 5 sutures, 5 plates. 1, 2, 3, 4, 5. And what I find also compelling in that figure, in blue here, the blue lines are meant to represent the seismic tomographic image of the lithosphere at the time he was publishing this paper. So basically what does he show here? Blue line that are supposed to represent the lithospheric structure. Do you think the green line follow the blue lines? No. This guy is just human histories of research. This guy was at the Institut de Physique du Globe, Institute for Physics of the Globe. But he was mostly a geologist. And he told just his geophysics guys, okay, your data, I don't care about it. I do what I want. That's what I read in that picture. Okay, so now we're going to... Yep. Sorry, because the air conditioning, I don't hear.
Could you explain once more the turning of the vector?
Yes.
Could you explain that one?
Again? Huh? So just explain, or I mean, just present the data. The data show that the vector direction changes from north-south to east-west, but at the same time, the norm of that vector diminishes where it crosses the topographic front, which means that material has been shortened in the horizontal direction and thickened in the vertical one. But there is also some motion lateral. And across the other topographic front here, the norm of the vectors changes and increases. That means that in between here and there, the material has been stretched and in vertical direction, thinned, shortened. I would see that. That's the last slide of the day. So we move from that idea of punching several times with extrusion laterally with another model that I'm going to develop with data analysis for the next hour, and then we have the conclusion. I can give you the conclusion right now if you want. But I think it's better if I build a demonstration. By the way, I think also through these lectures, you should feel that science is about demonstration, rational demonstration. So we might have different interpretations, but we rely on the same data. It's not always easy to decide what is really data and what is interpretation. But we try to be as objective as possible. And in my demonstration, I build a reasoning based on rationality and analysis of data. And what you learn when you're bachelor's is to acquire the methodology in order to acquire the data and the knowledge, the definitions, and then moving to master and doctoral programs, then you learn how to develop the technology, use the technology to demonstrate and answer questions scientifically. So the demonstration is a big part of it. It's not just giving data, right? So let's just go across the Himalaya Tibet, go through a few slides, and then we'll proceed with our demonstration. So in terms of topographic and geologic unit, you have the main central thrust. So there's the frontal thrust, the Gange plain, the Himalaya belt, and then the Tsangpo suture, in this Tsangpo suture. And we're going to also see some place at some point Ladakh in my presentation and in the one of Malika. And then we go into the plateau, the Tibet plateau. But in the Tibet plateau, there are several units that are separated by suture zones that are put in green here, that delimit crustal blocks, Lhasa block, Kyongtong block, Tsongpong Ganze, Kaidam block. And in between there is a zone of depression, the Tarim Basin. You also notice here alignment of lakes that corresponds to rifts, zones of horizontal stretching, but east-west. And that's somehow consistent with that, right? Okay. So that's the view with the blocks, Lhasa, Kyongton, Tsongpon Ganse, and Kaidam. And that's a similar view, that's 2000, Yin and Harrison 2000. Similar view than the one proposed by Taponnier, with juxtaposition of several wedges, each of them associated with closure of one ocean with one subduction. And another point here is that you see that crustal structures can be followed from the surface all the way down to the moor and even sometimes in the lithosphere. So crustal structures are representative of lithospheric scale structures. And the same is shown here. This we're going to challenge. It's not going to please geophysicists. No, but we're going to, yeah. Okay. I don't think we need to be much further with that. I also want to illustrate here that there is a long history. So after saying that there's a long history of tectonic accretion along that convergent plate boundary, there's also a long history of magmatism. And arc magmatism being related to subduction. So it goes all the way to 530 million years, and there is a migration from north to south. The oldest is there, and it gets younger and younger, and the latest one is the Trans-Himalayan or Ladakh batholith here, but the Trans-Himalayan batholith, its extension to the east, and that's the last events. That's DPEC is working on that. It's 40 million years, and that's the last magmatic event on that, which is north of the Indus Tsangpo suture. Yeah, so construction of this orogenic belt is not just the last 50 million years. It's a long history. It's not just the last collision between India and Eurasia. There has been several blocks in between and several continental oceanic sutures. In terms of geophysics, so we have here the Tibet plateau, the Himalayas, India, and that's the Bouguer gravity anomaly. So basically gives us the size of the thickness of the crust. So these are the data in the black dots, and the model here with only isostasy. So isostasy, it's like each vertical column is independent from the neighbors, right? So if I walk, well, the ground should go down, right? Because each individual column is independent from its neighbors. That's very idealistic, right? There is some strength, and we are working on a plate, which is not just vertical columns that I can move relative to each other. So there is some flexural rigidity to that plate. But the isostatic model, the red, is not that bad. No? It gives you the first order, especially in the zone of the plateau. It gives you the first order signature of the thickness of the crust. But especially on the foreland, on both sides, there is a need to take into account that flexural rigidity. And it's in the place where the plate bends. Then you need to take that, in order to account for that curvature, you need to take into account the rigidity of the plate. And that's for about, let's say, 150 kilometers. So, in other words, it's important to take that into account, the flexural rigidity of the plate, for wedges that are less than 200 kilometers wide. For belts that are wider than that, then it's pretty much isostatic compensation. So these are the view from receiver functions. I'm not going to go through the methods, but it allows you to identify in another way, check the depth of the moho. And it confirms that it's between 50 and 60 kilometers. And the moho is flat. Moho is flat beneath Tibet. That's an important point. And you also see that there are flat geophysical structures. And these corresponds to P versus S waves conversion. So it means that the material, the rocks underneath, they will propagate faster or slower the seismic waves. And these look like they are horizontal. So you see some obliquity here at the front, but then beneath Tibet, it's all horizontal. You don't see such things. You see it here at the front, but as soon as you reach Tibet, pretty much everything is flat, according to geophysics. So you don't see these structures that go all the way down from surface to the lithosphere. Again, except here, at the front. So in terms of lithospheric scale, again, so I had one person asking me already, she's not here yet. Yesterday, and she said, okay, from the seismic tomography, it was proposed that the slab here was overturned. Wouldn't it be simpler to have a slab subducting towards the south? Fine. Nobody has been there, right? Nobody was there 50 million years ago. And that makes perfect sense. So that's where I think that was a very good example of a person that was able to take a step out of the way of the mainstream. Because our ideas about India, Himalaya, Eurasia was very much controlled by the previous work. And everybody was saying subduction towards the north, but maybe that's not the simplest way to explain the tomography. And being researcher, a scientific researcher, is also has to do with your ability to build confidence in what you see and what you think. And it's also about your ability to step aside from the mainstream. No? You can reproduce, and most of us reproduce all our career long, reproduce the work of others, and that's fine, you know? And we need that, you know, to grow a corpus of knowledge. But at some point, if we want to move a bit forward, we need to have people that take a step aside.
Wouldn't it contradict with the fact that the Indian hemisphere is much more rigid than the Western?
Yeah. No, that's... Well, I think, to be honest, I think these images are difficult to interpret. And look at it. Huh? It's plus or minus 0.5% speed difference, velocity difference. That's not very much. Huh? And what I explained to that person yesterday, she's not here, huh? I don't think so. Huh? No. Is that the problem here with seismic wave propagation? So you compare the time of arrival of seismic waves with the time of arrival that is predicted by a 1D model. And all these squares here are cells. And the problem here is that it's the place on Earth where the crust is thickened. And the waves are going across that crust. So we do not get the waves directly from the mantle to the surface. We have to go, they go through the crust. So it's not like I see you now. You know, in between us, there is a crust. So I don't see you very well. And the thicker the crust, the more difficult it is to see what is underneath. So I think that's the problem here. And it looks like from the last 10 years, the seismic tomography is not making much improvement. We put a lot of hope into that, but you see that the resolution is not that great. So it was an important step forward, but now I think we're in a dead end with that. We need to develop other techniques to better retrieve the structures at depth. So let's take it as is for now. Especially it looks like here, you see the white dots, that's the Benioff plane, Modati Benioff. Looks like it's dipping towards the south. So I think there's something to it. Reconstruction, so let's take it back to 290 million years with low Russia, Siberia, so there's no Tibet yet. And India is connected to Gondwana at that time, and terrains are going to move from Gondwana through the Paleotethys subduction and then being accreted to Laurussia, Siberia. That's the South China Craton and the Indonesian Craton. So that's terrain starts to depart from, separate from Pangaea with the subduction of Paleotethys, opening Neotethys. Boom, that's it. It's been accreted. And then India is separated from Africa. And then this will result in subduction of Neotethys. And you see here there is India, but there's also Greater India. And we talked about that yesterday. And the Indian Craton is here, that's the rigid part. But ahead of it, there is a Pan-African crust with at least 480 million years old rocks that formed here in an extended margin after the Pan-African orogeny. But this has now disappeared. And really, we don't really know the size of that because it's disappeared. And again, the current day displacement is remarkably consistent with the long-term displacement of India relative to Asia, which is a south to north motion. Today we see the same. So now we're going to go through the geology. And what I found also interesting when looking at, so I've never been there myself. I've only been in the eastern side. I'll tell you about that in the last two slides, on the eastern side of the Tibet Plateau, and you'll see why afterwards. So I just rely on literature. But it looks like, from the literature, people, geologists, mostly focused on the Himalaya. And Tibet is not interesting. It's not interesting, it's flat, it's dull, right? Himalaya is for real geologists, the ones that are going with hiking mountains So at some point you think, okay, how much is about the performance of doing geology in high altitude and how much is about resolving problems? So the map, just show Himalayas. Tibet we don't understand. India, we don't care. But it's very representative of the state of mind of these persons. Okay, whatever. So we have here the main frontal thrust, the main central thrust with the high Himalayan crystalline map, and we're going to go through that later on. And then in blue, Tethyan sediments. So that these are the sediments that were in between India and Eurasia on the margins of the continent that have been deformed during convergence along the convergent plate boundaries. We see that north of that Tethyan sediments, there is a dome structure, and we see an example of the Somorari nappe here. And then there is a suture, the Indus Songpo suture in green, and in red, the Trans-Himalayan batholith. Okay? Do you know about this geology or not so much, finalement?
The first years are not familiar.
Okay. So we go through that. So that's the front, the foreland with the Gange basin, with river. And then it's active. So you have quaternary sediments that have been thrust over by Miocene sediments. And these are the foreland sedimentary deposits, the quartzite with pebbles and sandstones that result from erosion of the high mountain belt. And it's been deposited up front, but at the same time it's been involved in the mountain belt as it progresses. So that's here. And then as we go inland into the orogenic belt, then the thrusts start to pick up the sedimentary cover deposited on the basement. That's it. Here we have the Miocene, and boom, the Tethyan sediments thrust over the Miocene. So that looks fairly similar to what we showed yesterday on the Western Alps, right? With the foreland and then the cover decoupled from the basement. And then as we proceed, the thrust pick up still yet deeper and deeper units with fold and thrusts. And that has been followed all the way to the high Himalayan crystalline. And here we have the Proterozoic units, sediments that have been decoupled from the basement. And then we go into metamorphic rocks. So that's external zone, internal zone, compared to the Western Alps terminology that I gave you yesterday. And then we move to high-grade rocks, high-grade metamorphic rocks. And the boundary is the MCT. Okay, so it's metamorphic rocks on top of non-metamorphic rocks. That's consistent with the thrust. But you can also look at the structures in these rocks, and you see these schistosity and shear bands, C and S. That's consistent also with thrusting. And you can tell here that, that was enough for the geologists of the Himalayas. They stop their analysis there, right? Everything that goes to the east is not part of the story. And we have here an interesting feature that I'm going to show next. Okay, let's go across that structure of the high Himalayan crystalline. So first you have two different lithologies, orthognathis with photolith age of 480 million years, which is Ordovician, with a strong lineation. So that's representative of stretching of the rock. That's the x-axis of the strain ellipsoid. which is bare, which is on top of the foliation, and the foliation is the XY plane, perpendicular to Z, the shortening direction. That's how you reconstruct the strain ellipsoid in the field. And if you look parallel to lineation, perpendicular to the foliation, which is this plane, then you can see this CS fabric in a kyanite paragneiss, which is the other lithology of the high Himalayan crystalline. And it's also consistent with top to the north thrust. This is a nice map of all this lineation. And you see that here the turns also from north-south to east-west as the current day displacement. And this is old record. This record is probably 20 million years old, about 20 million years old. Okay, so we're looking at this unit, and it's been thrusted on top of the lesser Himalayan, the foreland, or the external zone. So now we're going to move to this place where there is a very interesting feature that was discovered about 40 years ago. The South Tibetan detachment. So you have here the high Himalayan crystalline, the thrust, the main sensor thrust, and on top of that, a normal fault, the South Tibetan detachment. And the resulting motion of the high Himalayan crystalline is sort of oblique extrusion in between a thrust and a normal fault. And that normal fault is also associated with localization of the pink here, which is a leucogranite. And leucogranite is here. So also, moving a bit too fast. First, I want to illustrate that here in this high Himalayan crystalline, you have kyanite-bearing rocks here, and sillimanite-bearing rocks here with leucosomes that bear garnet. So we have here everything to say that first we have kyanite and sillimanite. You see where they stand in the PT diagram. Kyanite is on the high pressure side, and sillimanite the high temperature. So there is somehow. So you can actually I can draw that. So it's somehow like this. Kyanite, sillimanite, andaluzite. And that's the solidus in presence of water. And if we add other, that's muscovite out, that's biotite out, and hornblende out. These are all the different solidus that can be activated during metamorphism of crustal rocks. So in other words, there might be an inverted metamorphic gradient here with high temperature rocks on top of high pressure, lower temperature rocks. So that's an image of the leucogranite that sits on top of orthogneiss with a protolithage of 480. Images of the migmatites of orthogneiss, migmatites of paragneiss, although it's difficult to tell what the protolith is, I think. I took that photo from Roberto Weinberg, who did that work in northwest India. But I'm not fully convinced it's an orthogneiss. Never been there, so I don't know. And then you have these leucogranites, boudinage leucogranite, which show a top to the north sense of shear. So this leucogranite, he's recording a top to the north sense of shear, marking the South Tibetan detachment to the north. Okay, so all these folded dikes veins reflect transposition and placement of veins during deformation. So the most transposed ones are the earliest veins, and the veins will be in place and then will be sheared, and as they are sheared, they start as like this to be folded and then eventually being totally transposed. We'll see that better tomorrow morning with the GIAN example. These are leucogranite. It's not like the batholith. It's not calc-alkaline magma with amphibole and it's you see all the brilliant spots are here muscovite, so it's an aluminum potassium-rich mica, which reflects probably a sedimentary source for the magma, so not a mantle source. Sedimentary source, crustal source. So these are the nice features that you can find with and play with the kinematics. And on top of that, you have this dike network on top of these leucogranites that are themselves, you see that's the leucogranite here, and it's been a bit pinched and swelled during deformation. And you see here the network of dikes that is better illustrated here. And the Himalayan geologist, where is he? He disappeared. Normally there's a red spot here. Maybe I cut the picture. Well, there is somewhere a geologist, maybe I cut for scale. No, the Himalayan geologist has to brag, has to say, okay, I was on top of the mountain, which is fine enough, it's fair enough. I'm just jealous because I never went there. And now we're going to move to that place, the dome region that is north of the South Tibetan detachment. And there you see it, so in between you have the Tectonic sediments that are folded, refolded. There we can still manage to identify the bedding, so metamorphic grade is less. So it's also consistent with the idea that this structure is a normal fault. It juxtaposes high-grade rocks that are coming from underneath, being exhumed, on next to low-grade rocks. So that's consistent with exhumation. So when you do these kinematics, rely both on structures and PT path. So that's the map of this region, and you see the Tectonic sediments, and then below that there is a nappe of high-grade rocks, the Tsomorari nappe, and then the suture with the contact with the suture with the ophiolite, and then the Trans-Himalayan batholith, this one. And it appears here, we were discussing that yesterday, on this paper they inferred that here it's also normal fault, which is consistent with higher grade juxtaposed to low grade. So we need to check again this paper, if it's well described or not. So this nappe, and Malika is going to expand on that, has recorded high pressure, low temperature metamorphism, eclogite facies, and even ultra high pressure, which is identified by the presence of coesite. Coesite is the quartz stable at ultra high pressure beyond 2 gigapascal, which means burial down to 100 kilometers. Maybe I'll take just a short break here to discuss that conversion between mineral pyrogenesis, pressure, and depth. See that? There are two steps there. How is it reliable? Well, basically what we say is that mineral reactions will record pressure, which is the weight of the rock column. Well, mechanics people, they tell us, we can have differential stress, and maybe what you're measuring is not only pressure, which is isotropic. Maybe you're measuring also the differential stress, sigma 1 minus sigma 3. And in some cases, it might be significant. So at first, petrologists said, no, we don't want to look at that because it's going to ruin our tool. We have a nice tool to go from minerals to pressure to depth, We don't want to look at the mechanics people, because they're going to ruin our tool. I think it's too bad. Because what you could do as petrologist, is to gain both the pressure and the differential stress. How to do that? Take samples in different structural positions. If you have a fold, in a fold you have inside of a fold and outside of a fold. Where should be the differential stress, the maximum? Inside or outside? Inside. Check if you have same mineral paragenesis inside and outside. Nobody has done that yet, so it's a future PhD. Same with boudinaged structures. Where do you expect to have the least pressure? In between the boudins or on the sides of the boudins? In between. So sample minerals in between the boudin's neck, and on the sides. Check if they are the same. Your reference frame is the structure, gives you a time frame, and then the pressure frame will be the minerals. If they are the same pressure, then, okay, we can use pressure as a scale for depth. If not, maybe you can have both pressure, depth, and differential stress. Does that, it's okay? So what, let's say we have pressure. If this is the case, then we can also date minerals that we think are associated with the mineral paragenesis. This is also tricky. I'm not going to expand on that too much now. But people that have done that say, okay, the peak pressure corresponds to mineral dated at 53 million years. And then there is a decompression, fairly isothermal, down to 50 million years, 47, and then 40 million years. And this retrogression is recorded by eclogite and blue schist. And also here you can also look at the structures and sample, relative to the structures. Well, usually these are not recorded in the same rocks. These would be mostly the mafic rocks, recorded the eclogite, and blue schist in the metasediments. And so in your sampling, that's for you, try to also check for different lithologic units that will tell you different parts of the story. And rely on structure for the relative timing. And then check with absolute timing. But we'll do that better with the Aegean example. And then in some places, they are on top superimposed, but below structurally, superimposed on the high pressure, low temperature, there is some hint of an increase in temperature. You see, not all the rocks follow that path. Some go like this, increase in temperature. And that's dated for this region around 13, 40 million years. And that's this arrow here. It corresponds to here. And this high temperature corresponds to domes, structural domes. Here the example of the Panma dome. But also metamorphic domes that are underlined or delineated by, so it's difficult to read here, but by metamorphic isogrades. That's a map. All these dotted lines are isogrades with the high temperature in the center, and then it moves down temperature centrifugally. So these are domes, structural domes, with high temperature rocks in the middle and lower temperature rocks on side. And the Tsomorawi nap, if I'm correct, is on top of that. Is on top of that. So the high pressure, high temperature, mid pressure, high temperature. That's another example with here the mineral paragenesis, K feldspar, garnet, biotite, sillimanite, nice prismatic sillimanite, and it goes all the way to these conditions, more than 700 degrees. And it's been dated at 6 million years for this particular example. There's also the same type of things to the east of the Himalayas in the Kangma, and all these are small domes. Right? These. Same thing, gneisses in the core, metasediments in the rim, and isogrades that are concentric, with high temperature in the middle, lower temperature on the side, and it's fairly mid-pressure, not high pressure. Okay, that's for the dome region. And on top of the dome, there are these Tethyan sediments, Tethys Himalaya, with folded trias. The bedding. Here, well, that's typical Himalayan geologist, with recumbent folds. And that's reproduced in that section here. That big fold here is this one. And you see, okay, so this can be reconstructed as probably as much in detail as in the Alps. There hasn't been so many geologists in this area as in the Alps, but the first order structure I think is fairly easy. If you accept the climbing, it's easy to reconstruct. So that's the South Tibetan detachment. And on top, you see that there is also shearing top to the north of the folds are consistent with shearing of top to the north. So it's also consistent with the South Tibetan detachment. Other examples of that in the Flysch or the Turbidite Cretaceous, the Jurassic. That's probably this part. And then the suture with the mantle rocks, Harzbergite, pillow basalts for the crust. Okay, so Malika is probably going to say, well, but it was Nitin. I was going to talk about that, Nitin. So I'm not going to expand, but that corresponds to the green line here. So that's really the oceanic crust and part of its mantle that has been trapped in between the continents. And then the batholith, the red part, granodiorite, diorite, enclaves, dated at 55 million years. That's the field area of Dipek. And then we enter the Tibetan plateau. Well, no wonder geologists didn't want to work on that place. So it's good for quaternarists. Flat-lying lacustrine sediments, flat. You see the Himalaya in the back. So not much is happening there. Are you not shocked by that? We're in a place where, India just hit a big punch in Eurasia. And you have flat-lying lake sediments. They might be very recent, but still. There, it's just eroding. Glacial deposits, aeolian deposits, fluvial deposits, rivers, just redistributing a bit the material at the surface. No hint of big-scale deformation. We'll come back to that. So let's go now through the different models. So the first one I mentioned is the wedge model that didn't consider Tibet as part of the picture. So in this model, at that time, the South Tibetan detachment had been recognized, so the idea was that material would come in the orogenic belt with decoupled from the basement, then would be buried and then exhumed essentially by erosion, with material point moving down and up according to erosion, and with some motion here of this along the South Tibetan detachment that would at some point here at depth meet the main central thrust and the main frontal thrust. So that's the wedge theory. And the other underlying idea here that there is an equilibrium between plate tectonic force and gravity. That's the shovel. And at some point, so at first, the wedge goes like this, goes like that. At some point, it reaches an equilibrium between gravity and plate tectonics. And it's also associated with redistribution of material by erosion. but you don't need to care about what's happening to the east in that model. Everything to the east is rigid, which somehow matches the fact that there is no deformation. This one, and it also explains the inverted metamorphism with high-grade rocks on top of low-grade ones. And this is illustrated in that model where high-grade rocks would go on top of low-grade ones, causing an inverted thermal gradient, which then is reflected by the inverted metamorphic gradient. And the metamorphic gradient is the fossil isothermal gradient, inverted thermal gradient. Well, in this model, there's a gate that is open here. Here you see the South Tibetan detachment doesn't reach the MCT. It's not clear what's happening, but it'll say, okay, maybe it's not that simple. So now let's take into account, because this model does not account for the Tsomorari. Because in this type of model, the rocks go down to, let's say, at most 50 kilometers crust. That's the thickest, or maybe we can go down to 70. That's not the case, what is represented here, but as the crust beneath Himalayas is about 70 kilometers depth, right? We can imagine that crustal rocks could go down there and go up, down to 70, but not more. So how do we get rocks that went to 100 kilometers, the Tsomorari rocks? This doesn't account for that. So people move to other type of models, the ones that I showed you yesterday, the Shemenda model, where rocks can be dragged with the lithospheric mantle down to 100 kilometers, mantle depth, and then decouple, move back to the surface. And that's represented here in that section of EPA and Steck 2008, where the Tsomorari went down to 100 kilometers and went up. So we change the scale, huh? Go from 50 to 100. So now I'm going to change a bit the angle of view, and we're going to look at what this high crystalline, high-grade nappes is made of. So it's made of mostly of mingmatites. I just showed you that before. Mingmatites and glucogranites are dated at 20 million years. These ones. The high temperature, low pressure, mid to low pressure rocks beneath the Tsomorari high pressure rocks are dated here between 10 and 6, if I take all of them, which is 10 million years younger, younger than the local granites. So let's take now a step into Tibet, and that's now how we're going to see how Tibet is related to the Himalayas. It's not disconnected, from my point of view. So this was presented in 95 or 96. Myself, I was doing my PhD, and at the time I was trying, as I explained to a few of you, was trying to test whether melting of orogenic roots could promote collapse of mountain belt. And I was working on rocks that have been exhumed from that orogenic root, and are mingmatites, granites. And here this team led by Nelson that shows geophysics beneath Tibet Plateau. What do they show? So we see here the MCT, the STD, and that's the dome region here, and that's Tibet. So the Moho is here, going down, but really what is shown here are different, there are two different types of geophysical data. That's seismic reflection, so that allows to follow structures, but you see that here we lose them. So again, the structures that are identified at the surface do not go all the way down to the Moho and not even to the lithosphere. There it's the other way around. Reflectors are here concentrated at about 10 to 15 kilometers depth, this high reflectivity zone. And this high reflectivity zone matches with the zone here, the blue, these are the seismic wave. So it's seismic refraction. So here the wave are going faster, faster, and then goes down here. See, there's up. You see that? That's a zone of low velocity. Not at the base of the lithosphere, within the crust. Within the crust, you have a low velocity zone that goes all the way almost to the moho. The moho is here. And you have a low velocity zone in the crust, which matches also with the high conductivity. And the top of this low velocity zone matches with the high reflectivity. So Nelson at the time, he was presenting that at the GSA meeting. I was there in the room. He said, okay, we don't agree in our team. We have geologists, geophysicists. We don't agree. Some think that these physical features reflect the presence of water at depth. Some think it's silicate melt, magma. I jumped on my chair. I said, I know what it looks like because I'm studying these rocks. I'm studying these rocks as they went exhumed back to the surface. Well, there might be some water, but it's a lot of silicate melt. That's for sure. I was really excited about that. I still have the goosebumps. And at the time, okay, some said, okay, maybe there is some melt, and that might be restricted to the zone because when they did their survey in the rift, in one of these rifts. So people said, oh, maybe there's some decompression melting just beneath the rift, but that's it. Well, if you look at the attenuation of seismic waves, that's the red part here, it's pretty much throughout the Tibetan plateau and all the way to the eastern side. So I think that's not something very limited to the rift, it's something that is big. You know? So that's our representation, but we pretty much followed the proposition of Nelson at the time, which shows here that all this zone of low velocity, high reflectivity corresponds to a partially molten zone. Is today partially molten. On top of which there might be concentration of glucogranites, magma. And how does that relate to this? Migmatites, glucogranite, 20 million years. Migmatites, granite, 10 million years. Partially molten rocks, magmas, today. That's exciting, no? I mean, and what does this mean? It means that the same process that we see here on rocks at the surface, now at the surface, probably was active there 20 million years ago. And 20 million years is the time at which these rocks crossed the solidus. They crystallized. So the first one to crystallize are now here. The second one, or the ones after, are in this dome region at 10 million years. If we wait another 10 million years, probably another dome here. Lateral flow of a partially molten orogenic root changes totally the perspective of understanding of orogenic processes. Right? So that means that you cannot restrict yourself to the understanding of the Himalayas. You have to take into account the full picture. What happens here? So that's the remaining questions. I'm not quite confident about that. Is where does this material come from? Because it's thick crust here. What are the solutions? It might come from the downgoing plate, if we accept subduction towards the north. So material that has been buried, forming high pressure naps, and then flow laterally on every side, on each side. Maybe we can invoke a southward subduction. Maybe we can invoke part of the Indian crust, or sorry, the Eurasian crust that has been shortened, but that's not consistent with the no deformation on top. It looks like it's been thickened from underneath the carpet. And the carpet has just been uplifted. So lateral extrusion so what is the main driving force? Yes, not tectonics, not plate tectonics. It's gravity-driven flow of partially molten crust, crustal root. And during that process, segregation of melt to form plutonic magmas that are going to form plutons on top. Okay, Malika, can it take another 5 minutes, 5-10 minutes?
Yeah, 5 minutes.
Yeah, okay. So, in order to test that idea, we designed a project with Julia de Sigoyer, who was also working on the Sommerari at the time. And we said, okay, if that partially molten crust has exhumed in the southern edge of the Tibetan plateau, is it possible that it also exhumes other places? So we said, okay, we're going to look at this place. Maybe the cream is coming out there too, right? And we built up a project that was twofold, was long-term behavior of orogenic roots with structure, petrology, geochronology. So that was our team. And the other team was short-term deformation of orogenic crust, looking at seismic data and GPS data. And at the time, so we designed the project, it was in 2002, 2003. The main motivating question is, why isn't there any earthquake there? Because there hadn't been any earthquake since historical times. Although the motion in between the Longmen-shan, that's the Longmen-shan, that's the Sichuan Basin with South China Craton. And there's a motion recorded by GPS between here and there, and so it's fast moving here, and there's no motion here. So obviously there's something happening, and there's something blocking here. Well, 2008, 7.9 earthquake. We had the answer. So the geophysics team had the answer. Why isn't there any earthquake? Well, it was just a matter of time. We just had to wait for 4 years. And it's been recurring, right? There's been recurrent earthquakes in this area. So what about us, the geologists? Well, so that earthquake is related to also a jump in the Moro from 40 kilometers to 63 kilometers. So basically, that's the crust that is thickened in this area and is currently thickening by thrusting at the front. Is it related to the Pacific? Or is it related to flow of that crust from north, that has been shortened on north-south direction and then flow eastward? We were really disappointed. We went into the Tsongpan Ganze, this area where you have high-grade rocks in purple, everything dated at around 200, 220 million years, nothing around Cenozoic. Well, that's also, you have to learn, when you do research, that's not everything work as planned. So then you build a very nice story, to get the funding. And then the work that you have to do is, well, the result is not answering the question I asked. So you need to find which question you have answered. Which is, it may seem a bit strange, but that's very often the case, especially for researchers like me. I'm very model-oriented, but I accept when the model is not confirmed that to find another model. And this is the work that you have to do, is to accept that, okay, you put your old model in the bin and you have to build another one. So we built another one with a story at 200 million years. What was nice is that with the thermochronology, so the temperature time evolution, so much of the history happened before 200 million years, but there is still a bit of a hint here, starting by a sort of a increase in temperature and then cooling, a last cooling from 400 to 0 degree during end of Mesozoic and Cenozoic. So that's during Himalayas, Tibet formation. Okay, what could that mean? So that cooling, these rocks that are today at the surface were at 400 degrees 60 million years ago. So that means that the isotherm 400 degree has been, the rocks that were there, has been exhumed to the surface. So there has been some uplift and exhumation. And they do not show much structures. A few faults, but nothing comparable to the amount of convergence and thickening that you observe in the Tibet plateau that goes from 30 kilometers to 60 kilometers. So you need to see structures that account for shortening of 100%, which you don't see. You see only faults that might account for 10% of shortening. So I think most of the thickening here happens by underneath the carpet. And the top unit is being uplifted and then eroded, exhumed, but thickening happens beneath the carpet. And that's what is shown in this picture here. That you have, it's schematized here as a channel that flows eastward and moves up the carpet. And that was first proposed by Lee Royden, and Clark. That shows here this view from looking from to the west with India, Himalaya, Tibet, and here the Sichuan basin. And they propose that here, that corresponds to a rigid block, and the lower crust is trying to flow around it, and that this pattern reflects that flow around a rigid block from underneath. I think that's marvelous, you know. It changes the perspective. We went from, again, from continuum mechanics, rigid geology, to fluid dynamics. It's much more, you know, much more soft. Okay, I'll leave you with that. So next step is what happens to this plateau? That's tomorrow morning, or yes, we decide that you have your lecture and then the exam, right? And to
I have my lecture tomorrow.
you have your lecture tomorrow, so the exam, or do I?
So if you only one more, that one, then the exam.
Okay, so okay, that's fine. So we start the history of what happens to the plateau. Okay. Take a break. Or questions? You're not too much shocked by this new story? Or did you hear about it? Did you hear about that story before or not? Not much, huh?
You want me to pass it around once more? Just to check.
Okay? So actually I decided not to go too much further. Maika is worried. I'm not going to tell the story of what happened to the plateau today. I'll leave it for tomorrow because it's already a big step from wedge to plateau. So I think it's enough in terms of new concepts for today. So tomorrow will be what happens to the plateau. But we'll still go to the Aegean area, which is here. It's the same Africa, Eurasia convergence setting, but a very different situation with some kind of a mountain on the edge, Crete, and the Hellenic Trench, and then an intermountain basin and another mountain on the side here. So an intermountain basin. In terms of seismic tomography, it also shows one single plate subducting towards the north. But look at it here. Here it looks like it's getting overturned. And there, I don't think I think we can discuss for the Himalaya, Tibet, about the polarity of subduction, but here it's fairly well constrained. And that goes all the way to the core mantle boundary. So it goes across the transition zones of the mantle. Above that slab, you have a zone of low velocity beneath the Aegean Sea. So beneath the Syria, there's a low velocity zone that might reflect some kind of weak mantle. In other words, an astenospheric mantle. So lithosphere here, an astenospheric mantle. And we'll see that this might reflect slab retreat, southward slab retreat, which was actually first identified by the geology, not by the tomography. We'll see that in the next slide. And in this area, no mountains. So at first, same models as for Tibet or even the Alps, actually. I didn't mention them from the Alps. Of continental collision, extrusion, except that here the free boundary is towards the west and not the east. And you see it's even more, I think it's even more compelling here. So the vector, that's GPS, and current depth displacement. The vector goes from north-south to east-west and even south-north. The norm of vector decreases passing the topographic front, which means shortening in the horizontal direction, thickening in the vertical direction. And here, the norm of vector, when it passes from the Anatolian plateau, there's another plateau here, that's a plateau, an orogenic plateau. The norm goes from small to very big. Well, that's peculiar for a punch. If I illustrate it with a punch, it's like if you had the head going out before the punch. You're feeling that I'm going to punch you in the face, so you go away before the punch. This moves faster than the punch. That's strange. That doesn't match the punch. What does it mean? Well, here we have a high topography, low topography. So the transition from here to there, in the vertical direction, what happens? See if you followed. Horizontal stretching, vertical thinning. No punch. At first sight, it might be tempting to say, okay, that's extrusion, lateral extrusion toward the west. And there's the Anatolian fault here, which is the most active fault in Europe current day. So it's very important to have a simple model that explains that. Well, looking at it more carefully, you see, the punch hypothesis, I think, is not that relevant. And people then have worked on this area and have identified that there is actually horizontal stretching, many basins here. All these lines are alignment of basins, sedimentary basins. And it's been exemplified by cross-section, structural cross-section, with here the Corinth rift. The Corinth rift is this one. And there's a high angle normal fault that here is proposed to route into a low angle detachment. And in Naxos, that we're going to look at in details tomorrow morning, here in the middle of the Aegean, there is a metamorphic core complex style with low angle detachment and high grade rocks exhumed beneath the detachment. So there is a lot of extension going on. Crustal extension. Other than that, if we look at the geology, so I'll put some colors on that map. I put them some colors that correspond to geologic units. So it's difficult to represent because there are different issues to be illustrated here. So most of these rocks are Tethyan units, sediments from the Tethyan margin, or the continental margin of Eurasia and Gondwana. The green ones are representing sutures. So that's one suture, which is called the Vardar suture to the north. And then here is the Pindos suture in the middle of the Aegean. So it has been debated whether these represents two different oceanic domains or it's the same that has been refolded and forming a single nap. I think now it's fairly, it's the main data confirm that it's two different oceanic zones separated by a continental ribbon here, another continent that's Eurasian margin, an ocean, a continental ribbon, another ocean, and another continental ribbon. And the oceanic crust is being subducted nowadays beneath the Hellenic Trench. In brown, these represent some of the basement of these continental ribbons, and they are Variscan. So they are inherited from the orogeny before It's okay? So here basically we have evidence for accretion of tethyon units to the Eurasian margins, continental ribbons, oceanic crust, making sutures that form this orogenic belt. The current day trench is here. That's the one that accommodates current day subduction. That's here. And in the rear here, you have thrusts, like ophiolite on top of continent. That's a thrust. But you also have normal faults. All these with squares or ticks are normal faults. Thrusts are cross-cut by normal faults. And you have also high pressure, low temperature units that are in the dark blue. Here, 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 in Crete. But also high temperature, mid pressure, low temperature, low pressure units in red. So you have a transition from high pressure to high temperature. And the high temperature postdates high pressure metamorphism. And if we look at it in northern part of the Aegean domain, in Rhodope Massif, the high pressure is 70 million years. High temperature is 40 to 30. And is structurally below, separated by a normal fault from the high pressure. In the Aegean, what dominates is the high pressure, but there are some high temperature rocks that I exhume in place to place. For example, here in Naxos, we're going to detail that tomorrow. Naxos here. And there the timing is 60, 55 million years for the high pressure, 20 to 30 for the high temperature. Another 20 to 30 million years delay between high pressure and high temperature. Same as for the Somorari and Dome region, you have 55 for high pressure and 15, 20 for 15, 20 for the high temperature. So a delay. So this will give us the opportunity to investigate the transition from low to high geotherm. And in terms of deposition, it's all the yellow. You have foreland basins, that's actually the brown, foreland basins. They are cross-cut by the yellow extensional basins. So you go from thrust-controlled basins, foreland basins, and then extension-controlled rift. But rifts very distributed. And it's all over the place. You have rifts, faults like that, faults like that. No, they also tend to be perpendicular to the, parallel to the convergence direction. Okay? That's for the setting. Yeah, that was the first evidence for retreat. This purple line, dotted line, represents calc-alkaline magmatism. And calc-alkaline magmatism is typically associated with subduction. And you know that alkaline or arc magmatism requires the plate to be subducted at a depth of about 100 kilometers, which controls the amphibolite eclogite transition. And this reaction releases water that will lower the solidus of the mantle, generate magma that are put on place. So you know when you have arc magmatism that at that time eclogite transition was at 100 kilometers below your feet. That's very convenient to reconstruct plate tectonics. So it was 40 million years here, 20 million years here, and it's today active. Santorini, very nice island, very touristic. Santorini is here and it's active volcano today. 40, 20, 0. So today, The amphibolite chloride transition is here, and it feeds the arc today. It lowers the solidus of the mantle here, promotes magmas that are going up there. How to explain that it was there at 20 and there at 40 million years? Well, just the idea is that the plate retreated like that as it converged. So it was not only retreat, it was also convergence with retreat. Because we know that during that time period, from 40 million years to today, Africa has been converging towards Eurasia. So you can have convergence. My elbows are getting closer to each other, right? But at the same time, retreat. In other words, the point of contact is not fixed. I'll skip that. Okay, what about the metamorphic record of that? So we're going to go into the Cyclades, the central west Aegean domain, and we move from here close to Athens, that's the capital of Greece, the Lavrion area. I'm not going to show Evia, we have very nice results there, and we're going to move to Naxos. So first we look at this area today, and tomorrow we'll move to Naxos. So here we have represented, well, the Pelargonian nappe. Here that's the Variscan basement, non-metamorphic during the Alpine orogeny, with pieces of the suture in green, the ophiolite nappe, and here contact with metamorphic rocks. That's the main contact with metamorphic rocks. So below, structurally, the Variscan unit, here you have metamorphic rocks that are alpine, and the protolith is mostly the Mesozoic sedimentary sequence, marble and schists. Where it's with blue lines horizontal, it's been only affected by blue schist facies, high pressure, low temperature. And you see there are some places where you have a superimposed metamorphism here with green lines, vertical, that corresponds to green schist facies superimposed on blue schist facies. Retrogression. You asked that the first day. What conditions for retrogression? That's retrogression. And in some places, so for most of the Cyclades, it's the case, blue schist and then green schist. Some islands have preserved only blue schist. And then, when you have crust like that, with purple and purple, that's blue schist, fairly, only rarely preserved, but most of it is blue schist overprinted by mid-pressure, mid-temperature, amphibolite, or green schist to amphibolite facies metamorphism. And all the way to migmatites in the core here of Naxos. So let's start first with this part. So that's a zoom of that. The Lavrio, Lorion in French, Lavrio in Greek. I'm not sure you're familiar with that, but people who like minerals might have heard that name. It's a famous place for minerals. And it's been also the place where the Greek civilization, the Greek antique civilization, digged all their metals to build boats, to make coins, money. So it's full of holes everywhere. You have to be careful, actually. When you walk there, sometimes, boof, there's a hole like this, and it's not, there's no panel to say, be careful. So you have to be careful. But actually, it was a chance. At first, we went there as a geologist, and we met an archaeologist interested in mining techniques. And that's another good example of interdisciplinary research. When archaeologists met geologists, it was wonderful. We went down in the holes. We had to take all the helmets, the lights, and things. It was difficult for me. I had a hard time to go in. And you have an history of two periods of exploitation in the antique, and even much older than that. It was dated to 16,000 years ago, so it's very old mining. And then the Industrial Revolution picked up on top of that. There, the galleries are pretty big, so I can walk in it. But the antique, that's impressive. The antique, sometimes you're in a gallery, that was digged for the Industrial Revolution, and you see just a hole like this 1 meter by 1 meter square, and these guys went inside. Well, I could go inside and I couldn't go down, back. I was stuck. And you see you can still see the trace on the walls of the guy that has been. That's impressive. And so we started to build a project that was not fully funded, unfortunately, but I thought it was very, very compelling with archaeologists, with the guy that was looking at the morphology of bones of people that worked, and we could find their bones, and you can find that they had very casualties on the shoulders, on the forget my names. They're everywhere. They had and so you can tell the condition of life of these people working these mines, 2,000, 3,000 years ago, and then the evolution also of methodology of ore extraction. It changed from fire-oriented to more crushing and then valorizing it outside the pit. But still, what we managed to do is, us geologists, because the guys that were doing archaeology, they would follow all the galleries and do a map of it, precise 3D map of that. And when they showed it to us, we identified the geology. And I'll show it to you indirectly. So what's happening here? So we have here a blue unit made of marble and schist, mostly blue schist. And a green unit that is in contact with the blue unit with here a red contact, and you can tell by its shape that it's fairly flat-lying. It's almost horizontal. And the blue is on top of the green, so these are clipper. And the green is mostly green schist facies, marble and schist. The same potolith, different metamorphic grade. So if you look at it on cross sections, it looks like this. So you have marbles folded and refolded with the schists. On top of marble and schist folded, refolded, but with mostly green schist facies minerals. These were blue schist facies with glaucophane, chlorite, fangite, epidote. So that's in a metavolcanic, which is this, which is actually this one. And here you have mostly chlorite and fangite, so low-grade green schist facies. And on top of that, you have the ophiolite map that is non-metamorphic. So we're not now going to look at the structure. So the structure it's not too much vegetation, so you can draw panoramic view, and what the technique for field geologists, I think, is to do the work in two different scales. When you have this type of area where you can read into the scenery, draw the panorama as well as you can from your interpretation, and then you're going to walk there and check if it's correct, and take measurements. And once you are there, you turn around and you make the panorama of where you were the day before, where you had taken measurements. So you have to make things in two steps. From far, and when you're far, you look at the rocks where you are standing, making measurements, and then you go where you, on the outcrop, turn yourself and make the panorama of the day before. So it requires to have good notes and a good memory. So this is why I could attest that we have a superposition of S1 related to F1, S for schistosity, F for fold, refolded by F2 with an axial planar schistosity S2, and refolded by F3 with an axial planar schistosity S3. So this doesn't show in the first glance from the panorama. So you have to take measurements then and make observations, detailed ones. So this was done throughout this area. I'm not sure we see all the data. No, it didn't represent all the measurements, but we pretty much covered everything here with measurements, structural measurements. And that's 50 kilometers by, so that's 50 by 50 kilometers. So these are the outcrop features. And if you don't look carefully, you might miss it. You say, okay, it's all the same schistosity. You have to pick up contrast in rheologic contrast between different layers. Here's more carbonate-rich layer and more mica-rich layer. And if you look at it carefully, you find this type of hinges. That's an F1 fold. And you see that if you follow this layer, it's folded here. It's folded here again. And this is not the same hinge as this one. So you need an F1 for this one and an F2 for this one. You need an F1 and then an F2 and you have to find the place where the F1 is preserved. Is that clear? Take some time to get your eyes used to it. Actually, the first time I did that work was doing my PhD. I invited my master supervisor, and we were in front of a panorama like this. I says, okay, I think there's F1, F2, F3. I say, stop, I don't believe you. He say, okay, I'm going to spend the day in the bar, and you're going to map this area, and we discuss it in the evening. He was right. I took all the measurements, and made all the. He was right. I was say, okay, that's experience. Maybe one day I'll gain that. So it's a matter of repeating these observations. Once you see it once, then you see it everywhere. By the way, I come back to that. In the previous models here, that was the trend in the 80s, 90s, 2000, and even now, is to look for these Marionnites. It's very important. I'm not saying it's not important. These Marionnites that mark very strong contact, localized deformation between units with very different histories are very important to identify in the field. What is the assumption here is that all the rest is rigid or non-deforming. See, these are blocks. These are units that do not change shape or almost not, a little bit here. When you look at these units, you find F1, F2, F3 at least. It's not continuous, it's not, it's very deformed. And this deformation tells you something that I'm going to expand on to now. So another example here with this marble and schist. So I drew that. So here it's not easy to find, but you see here an hinge. And it's refolded here, so that's F1, F2. And you see here a pattern of horizontal folds. So it's F1, F2, and F3 on one single outcrop. While not sure it shows very well. I think it's better from far. So you see it here, this, and you see here. That. Better example, but it's here only S2 and S3. S2 and then S3. Another one with F2 and S3 with gradients of transposition. Here the S2 is better preserved, and here you only see S3. And you have to catch these in the field. That's part of the structural analysis. And then what did we do? Well, we sampled the F1 fold hinges, the F2 fold hinges, trying to see if we could detect obliquity between S1 and S2. That's the key. And then between S2 and S3. Can we find that in the thin section? Yes, we can.
Can we say that the lineation of fold 1 and lineation of fold 2 are...
Axes, you mean, axes.
Yeah.
Yes.
They are perpendicular.
Yes, okay. Good point. When you have this type of fold interferences, that's called hook type. That means that the fold axes are parallel between F1 and F2. That's one possibility. But you can have everything between parallel or perpendicular. And perpendicular will give you, egg box type of an interference pattern or domes and basins. And if it's oblique, it's crescent shape. So here, I think we're lucky because the crescent shape is difficult really to decipher. Hook type is the easiest to identify. So we're lucky, and we'll see it's not by chance. We'll see that has a tectonic explanation. But it's a good point. Thanks for raising that. So can we find it? Yes, we can find S1 and relics of S2, and mostly here S3. And you see it's not underlined or delineated by the same minerals. But that's tricky. That requires a mapping, chemical mapping, of this. So we come back to that afterwards. But do you see the different schistosities marked by different minerals? So then the idea would be to pick up the composition of the minerals delineating one structure and pick up the composition of the minerals delineating another structure and see if they reflect different pressure temperature conditions. Wow, that's a lot of work. Very precise work. And you see it requires also even statistical analysis. Yeah, and the basic underlying assumption, so we're going to work here with chlorite muscovite. So it's chlorite muscovite. Exploit that mineral assemblage structure relationship in terms of PT conditions and path, PT1, PT2 with D1, D2, D3, and then how it relates to a tectonic scenario. We'll do that in the next few slides, but before I finish the geological tour. So we have the detachment. Look at that. That's this line. So on top, that's the blue schist with some volcanic rocks, basalts some basalts here you can still see the pillow. And when you break the pillow, you find glaucophane in it. So the rock has not been deformed, but glaucophane, which is the high pressure mineral, grew without deformation. So you find that here. And below that surface, you have the green schist. So that's the cross section. And when you go there, you have actually a gradient of deformation over a few tenths of meters, and then a sharp, very sharp contact. You start with malonite in the marbles with dolomitic layers that are boudinaged and asymmetrically deformed, with the asymmetry of the tails giving you the sense of shear. And on top of that, you have the same marble that is broken into pieces. So it means that we go from malonitic, ductile, to cataclastic, brittle deformation. What does that represent? When you go from ductile, and ductile is overprinted by brittle. So in terms of temperature and pressure, what do you think it means? Decreases. And is it consistent with burial or with exhumation? I love that. You're much better than my students. I'm going to stay here. Probably I've got some Indian mood. Because I never connect like that with my students. Never anymore. Strange, huh? No, I'm really happy with that. So let's go back now to So, at first, we followed that logic. And actually, just what happened, just in a few words, in terms of a human relationship. So we've been working with my friend and colleague Stéphanie Duchesne in Naxos since 2000 to 2010. But then we published, but not as much as we wanted. And there are other teams that were in very good pace and were ahead of us in terms of competition, scientific competition. So we decided to change area. And there was one student that came to my office, and he was finishing his bachelor, and says, okay, where can I spend good holidays doing both party and geology? I say, go to Greece. If you go to Greece, it's going to be hot in the summer, but you're going to have fun, and you're going to have very nice rocks on the beach. So he went there, and I say, okay, if you bring me back a few interesting samples, we might define a master project for you. And that was his master project. But he was not lucky, because at first we followed that strategy, core and rim, and didn't yield any result that was understandable. So what we did is to do a very precise mapping of these minerals, chemical mapping with the microprobe, the electronic microprobe, with one spot every, I don't remember the resolution, but it was for one mineral like that, you'll see you have tens of points. And this is the result. So here it only shows, so these are the white micas. And so that's 1 grain here, and these are the chlorite. White micas, chlorite. So I have 1 grain here, and see, boom, 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 boom. Every spot is an analytical spot. And even with these details, it's difficult to see zoning. And if you plot that into muscovite, pyrophyllite, celadonite, these are the different poles of the white micas, you see a shotgun, right? The analysis, these are the analyses. So that's where the trick is. You say, okay, from that very complex cloud of analysis, I'm going to make it simple. And that's a bit, I think, sensitive. Okay, let's say that all these that are in this corner, I know where they are, the position of these points. I put them in light blue, all the light blue. We say that all these are the same. And we do the same for these, the dark blue. That's the dark blue. And these are the green. Okay, and that starts to be more organized. Even though you can see there's a continuity in the analysis, you pretend it's discretized into 3 different compositions, which is wrong, right? We know. Myself, I was not convinced of that strategy when the guy that we were working with proposed it. I said, I don't like that, But still, we identified that the green, okay, can you see it? Where is the green compared to the blue? Is it outside or inside? So who's for inside, who's for outside? So inside. Inside. Outside. So see, that's not that obvious. Huh? If half and half, and third, and another third doesn't want to express himself or itself, it means that it's not that clear. Okay, we managed to convince ourselves that this one is inside, surrounded by blue. You might not be convinced. Discussion, debate. It's good. Oh, it's good. Same here. We managed to convince ourselves that this is inside, surrounded by blue. Same here, but it's not that obvious. I agree. Yeah? And that's where, in the thin section, you have the S1, S2. And actually, you'll see why, but I designated the green as S0. But I am not going to give you the explanation now, just a few slides afterwards. So for the chlorite, same. Difficult to tell which is into which. But okay, we tried to convince ourselves that this was S1 and this was S2. And that's for the unit that is on top, the blue schist. And the blue unit that is below, that's the one. I think there it works better. You have the... still, it's not... So the blue is supposed to be... The dark blue is supposed to be S2, and the light blue is S3. And I think it's right that here you have more dark blue than here. No, it should be the other way around. See, I'm not even convinced. Sorry, I'm too honest. But we managed to get that published. Or did I make a mistake? Because I just relabeled them this morning. Let me check. Yeah, that's right. Okay. So that's 2 and 3. Okay, I made a mistake. That's why. Because, I mean, I'll tell you the story. Because Christoph Schäfer, who did his PhD on that, he labeled them 1 and 2, even though they represent S2 and S3. I mean, okay, you're honest, you only see 2, so you label the first one 1 and the second one 2, but we know from field relationship that what you labeled 1 is already 2. So how are you going to explain to anybody else what you're doing? You know, if you label the second one 1, then the third one 2, that's not going to work. So I relabeled them. And did I do the same mistake here? So that's, yeah, same mistake, okay. So that's 2. And that's 3. Don't try to work too early in the morning just before the lecture. Okay. But that's a good test. No? Good test, and it was not working. Yeah, something wrong. So there's more light blue here, that's S2, and more dark blue here, that's S3. Whew. And S2 is better preserved in the chloride, in the core of the antiform, rather than on the flanks, where it's S3. That's much better. Huh? You're better convinced? So now what does it do? What we can get is what we call iso plate in the pressure temperature field. And what were we after? We were after finding the transition from high pressure to high temperature. So going from the blue schist to the green schist. What were we expecting? An increase in temperature going from S1 to S3, right? So we had a preconceived idea. And that's important because you'll see. So what happens? Well, the first micas, the ones that are porphyroclast, here, the green ones. They are here. So they can be anywhere along this equilibrium line. The composition of these white mica can be anywhere, and each line represents one mica. So that's a range of micas that can cover this full range of pressure temperature. But if you compare them with S1 and S2, these ones are on the higher temperature side. So the earliest ones are on the higher temperature side, which is the contrary to what we expected. So then I thought, because I'm used to make wrong reasoning, so I thought, okay, maybe I did something wrong in my reasoning. But then I had a lightning. Muscovite resists alteration, supergene alteration. What if this muscovite was a Variscan muscovite, not a metamorphic one, but a detrital one, coming from a Variscan granite that was eroded to feed that sediment? And the Variscan granite will yield high temperature muscovite. That's why I called it S0. Could find a solution to explain the data. And then you have S1 and S2 with decreasing pressure from S1 and S2. But fairly high pressure, low temperature field. And you mix that with the temperature given by the chloride. So we are here. The chloride gives the temperature. It's something like around, doesn't change much between S2, I forgot to relabel these ones. So that's S1 and S2. So there's a slight decrease in temperature. Yeah, that's this one. For the green schist facies, so the bottom unit, there you see a clear increase in temperature. going from S2 to S3. That's S3. So there's a clear increase in temperature. So there we are in business. S1, S2, slight decrease in temperature with decrease in pressure. That's at the higher structural level. And at the lower structural level, from S2 to S3, increase in temperature with decrease in pressure. So now we can put that into D1, T2, D3. So these are Hercynian grains, detrital grains, D1, D2, D2, D3. Let's put that into a pressure temperature path. So that's this study. So the upper structural level only recorded burial, peak metamorphism, and exhumation with a slight decrease in temperature, while the bottom structural unit followed pretty much the same trend up to S1, S2, and then a slight increase in temperature corresponds to S3. We have demonstrated the transition from high pressure to high temperature. And then we can translate that into pressure, temperature, time, deformation path, D1, M1, D2, M2, D3, M3. So how does that translate into a tectonic scenario? So this is the proposition, is that D1 records burial and asymmetric folds associated with burial as the F1 folds. F1, and then the F1 are overprinted by F2 with a reversal of the kinematics. And F3 is transposition of high pressure into high temperature. So F1, burial. F2, exhumation along the same channel with reversal of kinematics. That's still there are rocks that have been buried at the front. And the reversal of the kinematics happens inland with this high angle, so that's a steep dipping detachment. So that's, if we name the structures, this is a thrust. And this is a high angle, not a low angle, high angle, steep dipping detachment. And this is the last structure, which is low angle detachment. And this structure that most structural geologists and tectonics would call an extensional structure is actually contributing to build the orogen, associated with exhumation of units that have been decoupled. It's not very well drawn here. But I wouldn't draw it like this exactly, but still I think we can get the point. And then there is the last stage, still associated with retreat, that corresponds to low angle and post-orogenic extension. And this contributes to thinning the crust. This contributes to thickening the orogenic crust, even though it's an extensional shear zone. That's why I don't like these terms. And that's a superposition that we just drew, S1, S2, and S3. And during that period, there is burial and exhumation under low geotherm that preserves high pressure, low temperature rocks. And then at depth, so the high pressure, low temperature rocks are better preserved at the higher structural level. And at depth, the temperature increases, and that's where this transposition will occur. First with green schist fascias, and tomorrow morning we'll see how it goes into amphibolite fascias, even all the way to partial melting. And there you barely see any relics of this high pressure. Okay? So the last slide, this also allowed us, when we went into that's in the caves, in the galleries, allowed to find S1, S2, S3, and pyrrhotite, and also different type pyrite, different type of mineralization. So we could place the ore deposition into that tectonic framework. So we could find the primary ore that has been then reworked, and this has to go with the fluids as well. No? Reworked during several stages of deformation and metamorphism from F1 to F2, F3. So it's very important also for metallurgists to find, this will give you a guide also then for mining exploration or exploration. And we could find the last event is the last ores are iron, lead, and that was what was mined at first. This is iron and lead, and that's exactly in the detachment. That's why I was telling you, when they showed us the map of the galleries, it was a map of the detachment. And at some point, the detachment would be cut by a high-angle normal fault. Boom, the galleries would go down 10 meters. And we could trace that fault at the surface. Oh, that's why the galleries go down 10 meters. The guys, they were following the lineation of the detachment when they were digging. They knew geology. Probably empirically, but they followed the geology. Okay, that's for today. Does that answer your questions about structure, mineral? You see, it's tedious work, yeah? And you don't have to, if it doesn't work by the first step, you have to insist and really think about your data. So the next step, as I was telling you, would be to try to, with the same tool, microprobe, date or laser date the different minerals. And then you probably have, because argon will work on that type of minerals, and it probably will help, or rubidium strontium might also work, and we might probably get, let's say, 50 million years for S1, 40 for the S2, and 30 for the S3. I never tried that, but it was a question, yes?
With respect to this particular project, what can we interpret in terms of the geothermal gradient, with respect to the minerals?
Yes. So it was, at first, you see here, we go from, I think that's a 15 degree per kilometer geothermal gradient at the time of subduction exhumation. And we go to 25, 30 degree per kilometer geothermal gradient. So we double, the geothermal gradient has doubled. And it goes with doubling the thickness of the crust. And it's linear. The more crust you have, the more uranium, thorium, potassium will decay, and it's a linear relationship. If you double the amount of uranium, thorium, potassium, you double the temperature. But it takes 20, 30 million years to do so, and that's what we're going to illustrate on Friday morning. And you are the second year students, huh? First year, wow. I'm impressed. Thanks very much for your attention. Oh, you have more questions? There was one? No, but that's it? Okay. So I guess